Okay, we're going to look at example 3.4. This example will be showing us how do we apply the method of access to look at a bimolecular species. A plus B give us C. How do we going to find the reaction order for the individual species? So do note that the question state that it is a non-elementary reactions. So to determine, two set of experiments were run. So the first test whereby Cb naught is 120 mole per liter, which is much greatly in excess compared to Ca naught. So even if we have fully consumed the Ca naught totally, the Cb naught concentration will be dropped to maybe like around 194.5. So from 120 to 119.5, 114.5 is not going to change very significantly as compared to Ca naught. So we can safely assume that Cb, which is equals to Cb naught, which is constant. Okay, so now we have these points over here where Cb naught is greatly in excess. So the rate of consumption will then be K, which we also need to find, Ca alpha, Cb beta. But since Cb, like mentioned already, is constant, so we can group all the constant together, and that will give us a K prime Ca alpha. So by doing so, you see this is just become a unimolecular species where there's only one species of A, and we can use the integrated rate law method to determine the order. So let's use the integrated rate law method and assume that alpha is 1. So which means we assume a first order, and then we need to plot the function of Ca naught over Ca is K prime T. This is what we need to find. Okay, and we see that if this graph over here and we convert the Ca into all the different Ca into Ca naught over Ca, and then we plot it versus time, do we see we get a straight line or not? So we have be having this table over here that this is the time t and the concentration at the various time t. This is Ca naught, which is this is Ca naught over Ca. So for this 5.5 divided by itself will be 1. So you take, for the second one will be 5.5 divided by 4.7. So subsequently, if you take the ln of the Ca naught over Ca, you can have this table over here. And if we plot time t versus ln Ca naught over Ca, you will get a straight line over here. So this means that it is a first order reaction. So plot of t versus ln Ca naught over Ca gives a straight line. So assumption is valid, alpha equals to 1. So minus Ra equals to K prime Ca. Now we did not proceed further to solve for the value of K, because even if we know what is Cb naught, which is essentially unchanged, but we do not know what is beta, so we cannot solve for the value of K at this moment. We leave it to later, then we solve it. So with this, we move on to do the second test, where now Ca naught in return is excess compared to Cb naught. So we go back to the rate law equation again, where K Ca alpha is 1, Cb beta. Okay, alpha is 1. So now, because again Ca naught is greatly in excess, So CA is a constant, so we group them together as K prime prime, CB beta. So now similarly we assume that CB beta is 1, first order reaction. So similarly we have to plot ln CB naught over CB versus time t. Okay, and then if we plot it, we find that, so we construct the table over here. Similarly, this is CB naught over CB, and if we plot it, you find that we did not afford to get a straight line. You see, it's too far off from a straight line. Okay, this is supposed to be 1 and this is 0. Okay, if you plot this, you find that you did not obtain a straight line over here. So therefore, from here is not a first order reaction. Then we assume that beta equals to 2. So we have to plot 1 over CB minus 1 over CB naught versus time t. Okay, and then we have to similarly we have to construct the table out. This is CB, this is time t, this is 1 over CB. So 1 over CB minus 1 over CB naught, again we get 0, and subsequently we have the various value over here. So if you plot time t versus 1 over CB minus 1 over CB naught, you will obtain a very nice straight line over here. So this means that this plot is a second order plot. Is valid. So hence beta equals to 2. Okay, then can we go ahead and solve for the value of k? For now we can, because from the graph k prime prime, which is over here, k prime prime is 1.3976 times 10 to the power minus 4. Okay, and this is in liter per mole per second. So this is our k prime prime. But what is k prime prime? We have set from here k prime prime is kCa, and Ca is almost unchanged. So k times Ca, which is also kCa naught, is 1.3976 times 10 to the power minus 4 liter mole per second. Okay, and what is Ca naught? Ca naught is 140 mole per liter times your k, which is then equals to 1.3976 times 10 to the power minus 4 liter per mole per second. So k from here, if we solve k, you'll find that k has a value of around 9.983 times 10 to the power minus 7. Okay, liter square mole square per second. So can we use, then what about, since now we know what is beta, can we use the first test to go and determine what is the value of K from here? Yeah, we can. So why don't we try it? So K prime is K times CB beta, and we found that beta is 2 and CB is the same as is equals to CB naught. So this is CB naught square. And from our initial plot, what is our K? K is our K prime, 0.0146. So it's 0.0146 and it's a first order, so it's a per second. And CB naught for this case is 120 mole per liter square, 0.0146 per second. So we can find K to be 1.014 times 10 to the power minus 6. Similar will be liter square mole square per second. And we compare these two values over here. Okay, this is 1.014 times 10 to the power minus 6. This is 9.983. So these two are almost similar, right? They are actually within acceptable range. The difference is within acceptable range. So therefore we can conclude that no matter which method that we use, which test we use to find K, it should be the same. So if we find what is the rate of disappearance of A minus RA is K of CA and CB square. And what is K? K is, you can choose, depending on which one you want, you can use this K or this K, because since they are not very significant difference, so you can choose any one of them. Maybe I choose this 9.983 times 10 to the power minus 7 liter square mole square per second CA CB square.